We're finishing up with number 11 from the Taylor series, Worksheet 2, AP Review for BC. Number 11, we have a function that is defined by f of x given here for all x in the interval of convergence of the given power series. For part A, find the interval of convergence for this power series. So if we want to find the interval of convergence, we're going to go through ratio test, which is the limit as n approaches infinity for a sub n plus 1 divided by a sub n. So a sub n plus 1 means we're going to replace every n we see with n plus 1, so n plus 1 over 3 to the n plus 1 and then x to the n plus 1. So this represents a sub n plus 1. And then we divide it by a sub n. Dividing by a sub n is the same thing as multiplying by the reciprocal of a sub n. So we can take the 3 to the n plus 1 and flip it to the numerator, and the n plus 1 and the x to the n, we can bring it down to the denominator. So whatever this reduces to be, we know wherever this is less than 1 will be where the series will converge. So if we clean this up a bit, 3 to the n plus 1, 3 to the n will cancel out, leaving us with just 3 over 3 squared, and 3 over 3 squared will just reduce to be just 3 in the denominator. N plus 2 over n plus 1 will stay. X to the n plus 1 will cancel out with x to the n, leaving us with just x in the numerator. So as n approaches infinity, we see that this expression will just go to 1 because the degrees match, and we just take the coefficient, so 1 over 1. So we're left with just absolute value of x over 3 is less than 1, which means that the absolute value of x is less than 3, which means that x is between negative 3 and 3. So our center is at 0, and our radius is going to be 3. Now, we also need to we're trying to find the interval of convergence. So we need to test the endpoints. So we need to plug negative 3 into our rule of sequence and see if this will converge or not. So here's our rule of sequence. Plug negative 3 in for the x. So negative 3 to the n will cancel out with 3 to the n, but it still is going to leave us with negative 1 to the n. So negative 1 to the n times n plus 1 over 3. Now, this is going to be an alternating series. However, the condition is that this expression needs to, the sequence needs to go to 0. And as n approaches infinity, we see that this rule of sequence does not go to 0. So by the nth term test for divergence, we know this series will diverge, regardless of the fact that it's an alternating series. For x equals 3, the other endpoint, we can plug 3 into the x of the rule of sequence. Okay, the x of the rule of sequence, which is here, right? So n plus 1 over 3 to the n over 3 to n plus 1. The 3's will 3 to the n will cancel out, leaving us with just n plus 1 over 3. And we know that this series, this will also diverge because by the nth term test, we see that as n approaches infinity, this will jump to infinity. This will not go to 0. So we know both endpoints will diverge. So our interval of convergence is between negative 3 and positive 3. Part B. Find the limit of, as x approaches 0, of f of x minus 1/3 over x. So we can replace f of x with the first few terms of our function, of our polynomial. So when we do that, f of x gets replaced with 1/3 plus 2 over 3 squared x plus dot dot dot. And if we were trying to clean this up a bit, we can see that the 1/3 and negative 1/3 will cancel out. And even if I try to evaluate the limit at that point, I'm still going to get 0 over 0 because we have x's in the numerator and denominator. So what we can do is we can try and look to see if we can factor out this denominator, x out, or cancel this denominator x. So the way we do that is if we can factor x from the remaining terms in the numerator, then we should be able to get that to cancel out in the denominator and allow us to reevaluate the limit. So if I factor out an x from each of the terms, the first term is going to lose the x, but every term after that will still have an x. The degrees will just drop down by 1. So if we factor out the x, notice the x's can go away. And if we reevaluate the limit, notice that every term will drop out because every term has an x attached to it. So it will go to times 0 will just go away, leaving us with just this first term, this constant of 2 over 3 squared, which is 2/9, which is therefore our limit. Okay. Part C, write the first 3 non-zero terms and the general term for the infinite series that represents the integral for 0 to 1 of f of x. So we're trying to find the definite integral of f of x from 0 to 1. So f of x we have given to us here. We just need to find the definite integral from 0 to 1. So we can go through power rule and then plug in our upper and lower bounds. So here is the function polynomial that's rewritten out. The definite integral from 0 to 1 means we have to go through and find the antiderivative. So go through power rule. First term becomes x over 3. Second term becomes x squared over 2. Third term is x cubed over 3, and we keep the coefficients. And then we plug in the upper and lower bounds. So plug 1 in for each of the x's. We're left with 1/3 plus 1 over 3 squared plus 1 over 3 cubed plus dot dot dot. And the general rule is 1 over 3 to the n plus 1. Okay. All right, so there's our general term, and there's the first 3 non-zero terms that we found. And now we need to find the sum of the series given in part C. Okay, if we look at this here, we see that 1/3, each of the term is being multiplied by 1/3. So the ratio is 1/3, and 1/3 is less than 1. So we know that this is going to be a geometric series that will converge because the ratio is less than 1. And so if we want to find the infinite sum, we can just plug into our rule a sub 1 over 1 minus r. A sub 1 is the first term of our series, so 1/3. The ratio is also 1/3 because every term is being multiplied by 1/3. So 1/3 divided by 1 minus 1/3. 1 minus 1/3 is 2/3. 1/3 divided by 2/3, the same thing as saying 1/3 times the reciprocal of 2/3, which is 3/2. 3's cancel out. Our infinite sum, or sum of the infinite series, will be 1/2.